Welcome to This Explainer. Today, we're going to demystify container security, and we're doing it by taking a really practical step-by-step journey. We'll trace a container's path right from the very start of its build process all the way to actively running in production.
Okay, let's kick things off with a pretty staggering statistic. Did you know that roughly 8.5% of public container images actually inadvertently leak secrets? We're talking private keys, API tokens, just floating out there. That is a massive amount of sensitive data just waiting to be exploited.
So to make absolutely sure you don't become part of that statistic, we're going to build a defense-in-depth layer cake today. We'll follow the container lifecycle across 5 steps: securing the supply chain, scanning and content trust, container hardening practices, managing secrets securely, and finally, runtime security tools. Step 1. Securing the supply chain. We've got to start before execution. You see, a secure container starts way before it ever runs, simply because every single image layer is a potential entry point for malicious code. To lock this down, we absolutely need an SBOM, or a software bill of materials. Think of it as the physical shipping manifest for your container. In modern dev, a single container image can have hundreds of third-party packages packed inside. Without an SBOM, you literally have no idea what you're running in production.
And this is exactly where a tool like Sift becomes a total lifesaver. It crawls through all those image layers to identify and catalog every single installed package, its version, and its metadata. It basically gives you a perfectly clear, machine-readable inventory of exactly what's inside.
Moving right along to step 2, scanning and content trust. It's time to verify those contents.
All right, so now that we've got our shipping manifest, we need a border customs agent to verify the cargo is actually safe. We weaponize that catalog using a vulnerability scanner, like Trivy. It scans the image to expose any known common vulnerabilities and exposures, or CVEs. It breaks down the exact package, tells you the severity level, like high or critical, and even tells you which exact version contains the fix.
The whole point here is that catching these flaws early on the conveyor belts drastically reduces your blast radius. By integrating this into your pipeline, you can actually set hard policy gates, like if an image has a critical CVE, boom, the build automatically fails. It keeps bad code out of your production environments entirely, and honestly, it saves you from that dreadful 3 a.m. incident response call.
Step 3, container hardening practices. Let's reduce that attack surface.
Hardening is essentially the physical security practice of removing unnecessary doors and windows from your application. Because even trusted official images often run with some really risky defaults, like running as the root user. So we apply the principle of least privilege here. Run as a non-root user, drop unnecessary Linux capabilities so processes can't escalate, and mount the root file system as read-only so nothing can be tampered with.
Looking directly at how this builds in code makes it so much clearer. It's as simple as creating an app group and an app user, changing the folder ownership, and then explicitly setting the user right before executing. It is such a simple code change, but it radically improves your baseline security.
Step 4, managing secrets securely. We've got to keep those credentials safe. Look, you wouldn't lock a massive bank vault and then just leave the key under the welcome mat, right? Well, baking secrets, like database passwords or API keys, into your images or environment variables is just as dangerous. Because images are immutable and cached, a baked-in secret travels everywhere. It can easily be inspected and reverse engineered. And environment variables, they notoriously leak in crash logs and debug dumps all the time.
So what's the better solution here? It's utilizing Docker-composed secrets to inject those credentials securely at runtime rather than build time. Instead of relying on fragile environment variables, the secret is defined right in the compose file and then mounted directly into the container's file system as a temporary file.
And here is why that is so cool. Because the app is programmed to read the secret directly from that mounted file path. The credential never lives in the image history. It's completely invisible to a standard Docker inspect. The application seamlessly fetches the localized data exactly when it needs it and leaves absolutely zero permanent footprint. Finally, step 5, runtime security tools. Let's detect threats in real time. Because once your container is deployed, you can't just walk away. You need to set up the security cameras and a guard dog at the perimeter. It's really vital to understand this distinction. Static tools enforce the rules to block bad deployments from happening in the first place, but runtime tools act as your live detective. They observe real-time behavior to catch live anomalies, like a zero-day exploit, the very moment they happen. For instance, a powerful open-source tool like Falco observes system calls directly via the Linux kernel. With just a simple YAML rule, it can be configured to instantly trigger a priority alert if a suspicious shell, like bash or shell, is unexpectedly spawned inside a running container. It catches that malicious lateral movement instantly.
So, by combining all these steps, from supply chain SBOMs to scanning, hardening, isolating secrets, and runtime monitoring, you build a seriously formidable defense-in-depth framework. It puts you in control. But it all leaves us with one final absolutely critical question to ask ourselves. Your containers might be running, but do you truly know what they are doing inside that black box? Stay vigilant out there, keep learning, and I'll see you in the next explainer.